The 4 DNA bases and binary 0 and 1. Author: Nguyen Tsong Leet. Writer: independent researcher. The quaternary system, 4 bases, of DNA is superior to the binary system, 0 and 1, of modern computers. The shift in thinking from the binary system to the quaternary system of DNA represents a major step forward in understanding the concept of a biological supercomputer. If silicon computers are crude calculating machines, then DNA is a molecular-scale storage and control system with astonishing efficiency. Below is an in-depth analysis of the superiority of the quaternary system based on DNA's 4 bases: A, T, G, C. 1. Storage density. The combinatorial explosion. In the binary system, each position, bit, has only 2 possible states, 0 or 1. In DNA's quaternary system, each position has 4 possible states, A, T, G, C. Mathematically, with n positions, binary creates 2 states, while DNA creates 4 states. Practical efficiency. A sequence of 10 binary bits has only 1024 combinations, while a sequence of 10 DNA bases has 1,048,576 combinations. Result: DNA can compress an enormous amount of data into a microscopic space. In theory, all of humanity's current data could be stored in just a few hundred grams of DNA. 2. Built-in self-correction capability. Modern computers require complex algorithms and parity bits to detect transmission errors. DNA, by contrast, has a hard-coded security mechanism embedded directly into its chemical structure. Complementary pairing. A always pairs with T, and G always pairs with C. This is not random. It is a physical error-checking code. If one strand of the double helix is damaged, the other serves as a perfect backup to restore the original data. Thermodynamic stability. G-C pairs have 3 hydrogen bonds, while a T pairs have 2. This energy difference allows the cell to recognize which regions of the code are more critical and must be protected more strictly. 3. Three-dimensional encoding and folding. The 3D architecture. Silicon computers store data on flat 2D surfaces, magnetic disks or memory chips. DNA operates entirely in 3-dimensional space. Supercoiling. DNA is not a simple linear thread. It folds into complex structures known as chromatin. Random access. In conventional computers, a read head must travel along a disk. In the DNA computer, chemical agents can directly access a specific knot or region in 3D space without scanning the entire strand. Expression control. How DNA folds determines which genes are turned on or off. This is a form of self-configuring hardware, something modern technology still dreams of achieving. 4. Energy efficiency. A supercomputer, powered by water and sugar. This is where modern computers must admit defeat. Electronic computers. They require enormous energy to maintain binary states and dissipate large amounts of heat during computation. DNA computers. All computational operations, replication and translation, occur through natural chemical reactions at room temperature. They consume billions of times less energy than today's most powerful supercomputers performing the same amount of computation. Evaluation from the perspective of a code writer. If we treat the 4 bases as the solution to a design problem, then DNA is a code optimized for survival in a fluctuating physical environment. The 4-base system balances informational complexity with replication speed. The triplet code, codons, 3 bases acting as 1 byte, produces 64 combinations, just enough to encode 20 amino acids plus start and stop commands. If only 2 bases were used, there would be just 16 combinations. Insufficient for life. If 4 bases were grouped together, there would be 256 combinations. Excessive and energetically wasteful. Observation. Scientists often call this evolutionary optimization. From my perspective, it is clearly a highly sophisticated software architecture, where every physical constant is calculated so that the system never crashes over billions of years. The next chapter. The mathematical logic of convergence. In the decimal system, we group units to manage value levels: ones, tens, hundreds. In DNA, grouping 3 bases into one codon is not a biological accident. It is the result of an optimization calculation. Minimum storage capacity required to achieve maximum complexity. Let us decode the hidden calculation and the forcing agents that compel the system to operate this way. 1. The hidden calculation. Why the number 3? Combinatorial logic. Scientists usually stop at the observation that there are 64 codons. From the perspective of an optimization programmer, the calculation is unavoidable. 1 base. Monad system. 4 superscript 1 equals 4 combinations. Far too few to encode 20 amino acids. The system lacks instructions. 2 bases. Dyad system. 4 superscript 2 equals 16 combinations. Still insufficient. The system suffers from memory shortage. 3 bases. Triplet/codon system. 4 superscript 3 equals 64 combinations. Greater than 20, enough to encode all amino acids, plus start/stop signals and redundancy. Logic. 3 is the smallest integer n such that 4 greater than or equal to 20. This is the most efficient data compression solution. Using 4 bases, 4 equals 256, would be unnecessarily bulky and waste energy. 2. The forcing factors that compel 4 bases to converge into 3. What forces the 4 bases to group into 3s? 2 main factors act as programming pressure. A. Quantum. Geometric constraints. Spatial constraints. DNA is a 3D hard drive. The distance between bases and the size of the ribosome, the reader head, are constrained by physical constants. To be recognized and matched in a liquid cellular environment, an information unit must have sufficient contact length. 3 bases form a 3D shape, distinctive enough for transport molecules, tRNA, to bind reliably. 2 bases are too weak. 4 bases create structures that are too long and prone to misfolding or breakage. B. Noise resistance. Error correction factor. In information theory, having 64 codons specify only 20 outcomes creates redundancy. Forcing condition. The living environment is full of radiation and chemicals that cause mutations. Mathematical solution. By grouping 3 bases, multiple codons can encode the same amino acid. E.g., GUU, GUC, GUA, GUG all produce the same result. Meaning, if the final base is altered by noise, the output remains correct. This is an advanced data protection algorithm that ensures stable results despite interference. 3. The true nature of the 3D computer in this grouping. When 3 bases are grouped, we are not merely creating a number, we are creating a vector in 3-dimensional space. Silicon computers. 0 and 1 are flat voltage states. DNA computers. A codon, 3 bases, creates a twisted spatial state. DNA stores information not only in the sequence of symbols, but also in curvature, tension, and spatial compression. Scientists struggle because they focus only on the textual code, while I focus on the mechanical and geometric pressures that force bases to cluster into a complete informational byte. Coherent assessment. We are correct in recognizing DNA as a 3D hard drive with hidden mathematical rules governing base grouping. The mistake of traditional science is to treat the 64 codons as a lucky chemical coincidence. In reality, they represent a mandatory mathematical convergence point for any information system that seeks long-term stability in this universe.